Right now, it's 2026, and Earth is 4.5 billion years old. It has survived 5 mass extinctions. It has been struck by asteroids. It has been completely frozen. It has been so hot that there were no polar ice caps at all. It has been through all of that, and life kept going. But here is what has never happened in 4.5 billion years of Earth's history. One species took over the entire planet in under 300 years. That species is us. We have burned enough fossil fuel to measurably change the chemistry of the atmosphere. We have altered the nitrogen cycle. We have moved more rock and soil than all the world's rivers combined. Geologists will be able to see our existence in the rock record millions of years from now. A thin layer of plastic, radioactive isotopes and extinct species markers, all compressed into a single geological moment. We are, right now, in the middle of the 6th mass extinction. Not approaching it, in it. And this is just the opening scene. This documentary follows Earth from this moment all the way to the end. Not just the end of humanity, but also the end of life, the end of oceans, the end of the atmosphere, the end of the planet itself. Some of what you are about to hear will happen in your lifetime. Some will happen in 1,000 years. Some will happen in 1 billion years. But all of it is already set in motion by physics, chemistry, and the slow clockwork of the solar system. Earth has a timeline, and we know most of it. Let's go through it, from the beginning of the end to the very last second. The next 75 years are the most consequential in Earth's 4.5 billion year biological history. Not because of what the planet is doing, but because of what we are doing to it. Right now, the global average temperature is about 1.2 degrees Celsius above pre-industrial levels. That sounds small, but it is not small. The difference between the last ice age, when glaciers covered much of North America and Europe, and the world we live in today is only about 5 degrees Celsius. The planet does not warm evenly. The Arctic is warming roughly 4 times faster than the global average. Permafrost, frozen ground that has been frozen for tens of thousands of years, is melting and releasing methane, a greenhouse gas roughly 80 times more potent than carbon dioxide over 20 years. This is called a feedback loop, and it is already running. We are approaching several tipping points. Scientists have identified at least 9 major systems on Earth that, once pushed past the threshold, will change state permanently. Not in centuries, but in decades, and in some cases in ways we cannot reverse. The West Antarctic ice sheet, the Amazon rainforest, the Atlantic Ocean circulation current known as AMOC, the Greenland ice sheet. The Atlantic meridional overturning circulation is the ocean conveyor belt that keeps northwestern Europe warm and regulates rainfall across the Americas, Africa, and South Asia. Recent data shows it is at its weakest point in over 1,000 years. If it collapses, it does not gradually slow down. It tips, and when it does, the climate effects hit within years. Meanwhile, the biodiversity numbers are stark. Since 1970, just 55 years ago, we have lost approximately 70% of all wild vertebrate populations on Earth. Not species counts, but actual animal populations. The Amazon is approaching a tipping point of its own. Around 20 to 25% deforestation, the forest can no longer generate enough of its own rainfall to sustain itself. It begins to dry out and collapse into savanna. We are currently at roughly 17%, but here is the question that splits this century into two very different futures. Does civilization adapt, or does it not? If it does, if we decarbonize fast enough, if we halt deforestation, if renewable energy scales as it has been scaling, then by 2100, Earth stabilizes somewhere between 1.5 and 2.5 degrees of warming. That is painful and disruptive, but survivable. Coastal cities flood or are abandoned. Hundreds of millions of people migrate. Entire ecosystems are altered. But complex civilization continues. If it does not, if we continue on current trajectories without major intervention. We are looking at 3 to 4 degrees of warming by 2100. At that point, large parts of the tropics become lethally hot for extended periods. Food systems destabilize. The cascading tipping points begin firing one after another. This does not necessarily end civilization in 2100, but it sets in motion a collapse that plays out over the centuries that follow. This century is the test, and the result of this test determines everything that comes next for the human story. But here is the thing. And pay attention to this, because this is the entire context of everything that follows. Even if we pass the test, even if we do everything right from this moment forward, there is still an ending. Earth has a death sentence. It was written the day the solar system formed, and no amount of human ingenuity changes it. Humanity is just the opening act in a much, much longer story. Assume humanity survives the next century. What does Earth look like between 2100 and 10,000 years from now? If we stopped emitting all greenhouse gases tomorrow, completely, overnight. The planet would continue warming for several more decades due to heat already absorbed by the oceans. The climate system has inertia. Carbon dioxide that is already in the atmosphere takes hundreds to thousands of years to fully cycle out. Some of the warming effects we have already set in motion will last 10,000 years. The sea level rise we have already committed to, from ice that is already melting, will continue for centuries even in the best-case scenario. The West Antarctic ice sheet, even if we stop all warming today, may already be in the early stages of an unstoppable collapse. If it fully disintegrates, global sea levels rise by roughly 3 to 4 meters. That wipes out many of the world's most populated coastlines. It does not happen overnight. It plays out over 200 to 1,000 years. But the process, once initiated, cannot be stopped. Over the next several thousand years, the carbon dioxide in the atmosphere will slowly be drawn down by natural processes, chemical weathering of rocks, ocean absorption. But this is geological timescale chemistry. It is slow. Glacial cycles are worth understanding here. For the past 2.6 million years, Earth has been in what scientists call an Ice Age era, technically called the Quaternary glaciation. Within this era, Earth cycles between glacial periods, when ice sheets advance, and interglacial periods, when they retreat. We are currently in an interglacial called the Holocene. Without human interference, the next glacial period would begin somewhere between 10,000 and 50,000 years from now. But the carbon dioxide we have added to the atmosphere has likely delayed the next glacial period by tens of thousands of years. We may have accidentally cancelled the next ice age. Now, imagine the other scenario. Imagine humanity does not survive the next few centuries. Civilizational collapse, whatever the cause. What happens to Earth without us? Nature rebounds faster than most people expect. Within 10 years of human absence, cities begin visibly overtaken by vegetation. Within 100 years, forests reclaim large portions of farmland. Within a few thousand years, most physical evidence of our cities has begun degrading, though some structures, particularly concrete and stone, would persist for tens of thousands of years. Plastic will persist in ocean sediments for millions. Within 5 to 10 million years, most traces of human civilization would be geologically erased, compressed into that thin, anomalous layer in the rock record. New species would have radiated to fill the ecological niches we and our domesticated animals once occupied. Life, as it has done 5 times before, would rebuild. But here is the cliffhanger built into both scenarios: human survival and human extinction. Neither outcome changes what is coming next, because what is coming next is not driven by us. It is driven by geology. We are now outside the range of anything humans have ever experienced. 10,000 years ago, agriculture was just beginning. 100,000 years ago, modern humans had not yet left Africa. We are now looking at timescales that dwarf all of recorded and pre-recorded human history, multiple times over. On these timescales, the forces that matter are geological and astronomical, not biological. First, ice ages. As discussed, human emissions may delay the next glacial maximum, but they will not prevent glaciation indefinitely. Eventually, somewhere in the range of 50,000 to 100,000 years from now, ice sheets will advance again across the northern hemisphere. Glaciers a kilometre thick will sit on top of what are now New York, London and Moscow. The ice will grind mountains down, reroute rivers, reshape coastlines. This is not catastrophe. This has happened over 50 times in the past 2.6 million years. Life survives. It migrates toward the equator. When the ice retreats, it follows. Milankovitch cycles drive these ice ages, small, predictable variations in Earth's orbit and axial tilt that shift how much solar energy different parts of the planet receive. These cycles operate on timescales of 23,000, 41,000 and 100,000 years. They are as reliable as clockwork, and they have been setting the rhythm of Earth's climate for millions of years. On these same timescales, the continents are still moving. Not fast enough to notice in a human lifetime, the plates move at roughly the speed that fingernails grow, a few centimeters per year. But over tens of thousands of years, this adds up to kilometers. Over millions of years, it reshapes the map of the world entirely. In 10,000 to 100,000 years, the changes are minor compared to what is coming. But the motion is constant, accumulating, building toward the dramatic reorganizations that will come later. There is one more thing lurking in this chapter, something that has a roughly 1 in 10,000 year chance of happening at any given time, and therefore a near certainty within this window: a major asteroid impact. The last extinction-level asteroid impact was 66 million years ago, the one that ended the dinosaurs. But large impacts, while rare, are not absent. An asteroid roughly 1 kilometer wide strikes Earth approximately once every 500,000 years. An asteroid roughly 10 meters wide, large enough to flatten a city, strikes somewhere on Earth approximately once every 200 years. We have been building asteroid detection and deflection capability since the early 21st century. The question of whether future civilizations or no civilizations are watching the sky when the next one comes, that question has a very different answer depending on what happened back in Chapter 1. Assuming no major impact, life continues. Glaciers advance and retreat, continents drift, and then, around the 100,000-year mark, something wakes up. There are places on Earth where the crust is thin, not just thin, but actively bulging upward from below, heated by a mantle plume or sitting above a massive magma reservoir. These are called supervolcanoes, and they do not erupt the way normal volcanoes do. A normal volcanic eruption, Mount St. Helens, Pinatubo, injects some ash and sulfur into the stratosphere, causes a year or two of slight global cooling, and that is it. Devastating locally. Globally manageable. A supervolcano eruption is categorically different. The last supervolcanic eruption on Earth was Toba, in what is now Sumatra, Indonesia. Approximately 74,000 years ago. The Toba eruption ejected roughly 2,800 cubic kilometers of material into the atmosphere. For comparison, the entire Mount St. Helens eruption in 1980 ejected about 1 cubic kilometer. The Toba eruption may have pushed the global human population down to as few as 10,000 to 30,000 individuals, a genetic bottleneck you can still see in human DNA today. It caused a decade-long volcanic winter. Global temperatures dropped by 5 to 15 degrees Celsius. There are at least 5 known supervolcano systems on Earth currently active at various levels. Yellowstone in the United States, the Campi Flegrei caldera in southern Italy, Toba itself, Lake Taupo in New Zealand, the Long Valley caldera in California. Yellowstone has erupted on a roughly 600,000 to 700,000 year cycle. The last major eruption was about 640,000 years ago. The next major eruption could be tens of thousands of years away, or it could be hundreds of thousands of years away. There is no reliable way to predict supervolcanic eruptions on the scale of centuries, let alone millennia. What is certain is this: within the next million years, at least one of these systems will almost certainly erupt at supervolcanic scale. Maybe more than one. A Yellowstone-scale eruption today would inject so much sulfur dioxide into the stratosphere that it would block sunlight for years. Global agriculture would collapse. Global temperatures would drop catastrophically. Any complex civilization present at the time would face an existential threat. Any surviving ecosystems would be severely pruned. Life would survive. It has survived every supervolcanic eruption in Earth's history. But nothing above a certain complexity threshold would remain unchanged. Over the span of 1,000,000 years, the Earth begins to look genuinely alien compared to today. Multiple ice age cycles have carved new landscapes. Species that exist today are gone, replaced by evolutionary descendants adapted to a changed world. And the continents have moved far enough that their positions are measurably, visibly different. But the real geography change is still coming. The African continent is tearing itself apart. The East African Rift System, a network of geological fractures running from the Afar Triangle in Ethiopia all the way down through Tanzania and Mozambique, is not a metaphor. It is an active rift zone where two sections of the African plate are pulling away from each other at a rate of a few millimeters per year. Today it has produced the Great Rift Valley, one of the most biologically significant landscapes on Earth, and very likely the cradle of human evolution. In roughly 5 to 10 million years, the rift will have spread far enough that the Horn of Africa and the eastern portion of the continent will separate completely from the main body of Africa, forming a new island continent. The Indian Ocean will flood in, and there will be a new sea where the rift now sits. This is how ocean basins are born. The Atlantic Ocean started exactly this way, as a rift between what was once a single supercontinent. Over millions of years, the rift widened, flooded, and became an ocean 3,000 miles wide. Meanwhile, the Mediterranean Sea is in the process of closing. Africa is slowly moving northward, colliding with Europe. The Alps are rising as a result of this collision. The same process that built the Himalayas when India collided with Asia roughly 50 million years ago. In another 50 million years, the Mediterranean will largely be gone, replaced by a mountain range that will dwarf the Alps. Australia, meanwhile, is moving northward at roughly 7 centimeters per year, fast by geological standards. In about 50 million years, it will begin colliding with Southeast Asia, forming new mountain ranges and fundamentally altering ocean circulation patterns in the Pacific and Indian Oceans. Ocean circulation matters enormously. The arrangement of continents determines how ocean currents flow, which determines where heat is distributed across the planet, which determines climate patterns, rainfall, and habitability for every living thing on Earth. Every time the plates rearrange, the climate rearranges. Every time the climate rearranges, life rearranges. In 50 million years, the evolutionary descendants of today's animals, whatever they are living on a planet whose continents, oceans and climate are fundamentally different from ours. But they are still recognizably Earth organisms. They still breathe oxygen. They still drink liquid water. The basic conditions for complex life are still intact. That will not always be the case. because about 200 million years from now, all of this drift arrives at a destination. All roads, all plates lead to one place. Earth has had supercontinents before. Roughly 300 million years ago, all of Earth's land masses were merged into a single supercontinent, Pangaea. Before that, there was Rodinia, about 1.1 billion years ago. Before that, other supercontinents whose names are known only to specialists. The supercontinent cycle is one of Earth's most fundamental rhythms. Roughly every 300 to 500 million years, the continents come together, and then they break apart again. The next supercontinent has already been modelled by geologists. Most models predict it will form somewhere between 200 and 350 million years from now. Some call it Pangaea Proxima. Some call it Amasia, because in several of the models it is the Americas and Asia that collide first over the closing Arctic Ocean, and Africa and Australia eventually join them. The formation of a supercontinent has dramatic consequences for life. When all land is concentrated in one place, the interior of that landmass becomes extremely dry, far from any ocean moisture. The climate of a supercontinent is harsher than anything on our fragmented Earth. Seasonal temperature swings become extreme. Large portions of the interior become hot, arid desert. The oceans also restructure. One large ocean surrounds the supercontinent. Marine life is profoundly affected as the shallow coastal seas, the most biologically productive marine environments, disappear where continents merge. Every major mass extinction in Earth's history has been associated with large-scale geological events. Volcanic activity, sea level change, atmospheric disruption, and supercontinent formation is one of the most geologically disruptive events possible. Life adapts. It always has. But adaptation requires time, and mass extinctions are the price paid for not having enough of it. In 250 million years, life on Earth is still fundamentally biology as we know it, carbon-based, water-dependent, oxygen-breathing. The specific organisms are completely unrecognizable to us, but the mechanisms are the same: DNA, evolution, food webs, predators and prey. But the Sun is now roughly 250 million years older, and the Sun, over time, is getting brighter. And that changing Sun is starting, very slowly, very quietly, to create a problem that no amount of biological adaptation can solve. Here is a fact about the Sun that most people do not know. It is not constant. The Sun is a main sequence star, and main sequence stars slowly increase in luminosity as they age. As hydrogen in the core is converted to helium, the core contracts, heats up, and the outer layers expand slightly, increasing the Sun's total energy output. Over the 4.5 billion years since the solar system formed, the Sun has increased in brightness by about 30%. It is currently increasing at a rate of roughly 1% every 100 million years. That does not sound like much, but over hundreds of millions of years, it becomes decisive. The first consequence begins around 300 to 500 million years from now, and it is not what you would expect. You might expect the planet to get hotter first, but the first thing that happens is the plants die. Here is why. As the sun gets brighter, it slightly warms the planet. This slight warming speeds up a chemical process called silicate weathering. Rocks containing silicate minerals react with carbon dioxide and water to form carbonates. As the planet warms, this weathering process accelerates, pulling carbon dioxide out of the atmosphere faster than volcanic activity can replenish it. Carbon dioxide in the atmosphere has been declining for hundreds of millions of years as a result of this process. Today it is around 420 parts per million, high by recent standards, but actually low by the standards of most of Earth's history. 500 million years ago, carbon dioxide levels were probably 10 to 20 times higher. The problem is that plants need carbon dioxide. Photosynthesis is, at its core, the process of pulling carbon dioxide out of the air and turning it into sugar using sunlight. Most plants on Earth today use what is called the C3 photosynthesis pathway, and they need a minimum carbon dioxide concentration of about 150 parts per million to survive. Around 300 to 600 million years from now, atmospheric carbon dioxide will fall below that threshold. First, the trees go, then the grasses and most flowering plants. Some plants use a more efficient photosynthesis pathway, C4, that can function at carbon dioxide concentrations as low as 10 parts per million. These plants will hold on longer, but eventually even they cannot survive. When plants die, everything that eats plants dies. When herbivores die, carnivores die. The food chain does not partially collapse. It collapses from the bottom, completely, systematically and permanently. No complex animal life survives this. There will be no dramatic extinction event, no asteroid, no supervolcano, no mass die-off in a geological instant. It will be a slow fade played out over millions of years. Ecosystems will simplify. Megafauna will disappear first, then smaller animals, then insects, then the last multicellular organisms, unable to sustain themselves without the carbon base that plants have always provided. By roughly 600 million years from now, the only life left on Earth is microbial. Single-celled organisms, bacteria, archaea, in soils, in rocks, around hydrothermal vents on the ocean floor. The world of complex life that evolved over 500 million years is over, not from a single catastrophe, from chemistry. The oxygen in Earth's atmosphere was put there by life. That is not a metaphor. It is a literal fact of planetary chemistry. Before photosynthetic organisms evolved, roughly 2.4 billion years ago, Earth's atmosphere contained almost no free oxygen. The great oxidation event, when cyanobacteria started releasing oxygen as a metabolic byproduct, fundamentally transformed this planet. It was, by some measures, the largest environmental catastrophe in Earth's history for the organisms alive at the time. Oxygen is chemically reactive and toxic to many anaerobic life forms. Most life at that time died. But from the survivors, all complex life, including us, eventually descended. The oxygen we breathe today exists because living things, mostly plants and photosynthetic marine organisms continuously produce it. Take away the photosynthesis and you take away the oxygen supply. As the carbon dioxide crisis kills off plant life, between 300 and 600 million years from now, the oxygen production rate drops. But oxygen does not disappear instantly. There is a large existing reservoir in the atmosphere, currently about 21% of the total. It takes time for chemical reactions and biological respiration to consume it. However, without photosynthesis replenishing the supply, the oxygen levels will decline. Over millions of years, the timescale is uncertain, but models suggest somewhere between 600 million and 1 billion years from now, atmospheric oxygen drops to levels too low for complex aerobic life. Any animal life that has somehow survived the collapse of plant food chains would face this final atmospheric barrier. Without sufficient oxygen, aerobic respiration cannot sustain complex multicellular organisms with high metabolic demands. By approximately 800 million to 1 billion years from now, the atmosphere is back to something closer to what it was before the Great Oxidation event, low in oxygen, increasingly dominated by other gases. The complex biosphere, 500 million years in the making, has been undone. What remains? Microbes, some photosynthetic, some not. Extremophiles in hydrothermal vents. Chemolithotrophs, organisms that derive energy from chemical reactions in rocks rather than from sunlight. The deep biosphere, which extends kilometers into the crust, persists. Earth is not dead, not yet. It is back to where it started, a microbial world. A world that looks from space nothing like the blue and green planet we know. But the sun has not stopped getting brighter. And what comes next is the event that truly ends Earth. 1 billion years from now, the sun is approximately 10% brighter than it is today. That 10% increase in solar output is enough to trigger what climate scientists call a moist greenhouse effect. Earth's surface temperature has risen enough that the rate of water evaporation increases significantly. Water vapor, which is itself a greenhouse gas, creates a feedback loop. More heat causes more evaporation. More water vapor traps more heat. More heat causes more evaporation. This is not a gradual warming. Once the feedback loop initiates past a certain threshold, it accelerates. The oceans begin to evaporate in earnest. This process may take tens of millions to hundreds of millions of years to fully play out, but once it starts, it cannot stop. There is no natural cooling mechanism that can reverse it on Earth's surface. The carbonate-silicate cycle, the geological thermostat that has kept Earth habitable for billions of years, requires liquid water to function. Take away the oceans, and you take away the thermostat. As the oceans evaporate, water vapor rises into the upper atmosphere. High up, in the stratosphere, ultraviolet radiation from the sun breaks water molecules apart. Hydrogen and oxygen dissociate. The hydrogen, being the lightest element, escapes to space. It is not captured. It is gone permanently. Earth is losing its water to space. This is not a new idea. It is the same process that happened to Venus. Venus and Earth are nearly identical in size and composition. They formed at approximately the same time from the same material. Early Venus may have had liquid water on its surface, but being slightly closer to the Sun, it reached the moist greenhouse threshold earlier. Its oceans evaporated. The water was lost to space. And now Venus has a surface temperature of 465 degrees Celsius, a crushing carbon dioxide atmosphere 90 times denser than Earth's, and no water at all. Earth's fate in roughly 1 billion years is to become Venus. The timeline is not precise. Some models suggest the oceans could last until 1.5 or even 2 billion years from now if geological carbon drawdown proceeds at the right rate. But the endpoint is not in question. The last liquid water on Earth's surface disappears. The planet is now a hot, dry, geologically active rock with a dense steam and carbon dioxide atmosphere. Surface temperatures are high enough to melt lead in some models. Any microbe surviving in the deep crustal rock may hold on for longer, protected from the surface heat. But even the deep biosphere has a limit. Earth's ocean, a continuous body of liquid water that has existed in some form for at least 4 billion years, is gone. And the Sun is still not done. Earth's magnetic field is generated by the movement of liquid iron in its outer core, a process called the geodynamo. The outer core is liquid because the Earth's interior is still hot from the heat of formation and ongoing radioactive decay. But the Earth is cooling. It has been cooling since the day it formed. Slowly, very slowly, the liquid outer core is solidifying outward from the inner core. As it does, the temperature difference that drives convection in the outer core decreases. The geodynamo weakens. In roughly 2 to 3 billion years, models suggest Earth's magnetic field may begin to significantly weaken and eventually cease altogether. This matters enormously for whatever remains of the surface. The magnetic field is the planet's shield. It deflects the solar wind, a continuous stream of charged particles from the Sun, away from Earth. Without it, the solar wind would directly interact with the upper atmosphere, gradually stripping it away. This is almost certainly what happened to Mars. Mars lost its magnetic field roughly 4 billion years ago, and since then the solar wind has been systematically eroding its atmosphere. Today, Mars's atmosphere is less than 1% as dense as Earth's, and it is still being eroded. Without a magnetic field, Earth's remaining atmosphere, already dramatically different from today's, mostly carbon dioxide and water vapor, begins to be stripped away by the solar wind. The rate is slow by human standards. It takes hundreds of millions to billions of years. But there is no mechanism to stop it. By approximately 3 to 4 billion years from now, Earth's atmosphere has been largely stripped. The surface is exposed to full solar radiation, not filtered, not deflected. Combined with the surface temperatures already extreme from the brightening Sun, the planet is, by any definition of the word, dead at the surface. There is one more event to consider in this time frame, and it is the most visually dramatic event in the solar system that does not involve the Sun directly: the Andromeda Galaxy collision. The Andromeda Galaxy, 2.5 million light-years away, is currently approaching the Milky Way at roughly 110 kilometers per second. In approximately 4 to 5 billion years, the two galaxies will begin to merge. This sounds catastrophic, but it is not what you might imagine. Galaxies are mostly empty space. The individual stars are so far apart that stellar collisions are rare even during a galaxy merger. The Sun's chances of colliding with another star during the Andromeda merger are estimated at less than 1 in a million. However, the gravitational dynamics of the merger could alter the orbits of stars, including the Sun. There is a small probability, roughly 3% by some models, that the Sun could be flung to a completely different region of the merged galaxy, or even ejected entirely. If that happens, the entire architecture of the solar system changes permanently. But in the remaining 97% of scenarios, Earth is still orbiting the Sun. A Sun that by 4 billion years from now is entering the final phase of its life. The Sun has been burning hydrogen in its core for 4.6 billion years. It has roughly 5 billion years of hydrogen left. But the final stages of a star's life are not simply a slow fade. As the hydrogen in the Sun's core runs low, the core begins to contract under gravity and the outer layers begin to expand. Over roughly the next billion years, the Sun will increase in size and luminosity far more dramatically than the gradual increase we have been tracking. This process accelerates. Around 5 to 5.4 billion years from now, the Sun's core hydrogen is depleted. The core contracts. The outer layers expand outward. The Sun is entering the red giant phase. During the red giant phase, the Sun will expand to roughly 100 to 200 times its current diameter. Some models suggest up to 250 times. Its surface temperature drops, giving it a redder color. But its total energy output increases dramatically, hundreds of times current levels. Mercury is consumed first. At maximum expansion, Mercury's orbit lies inside the Sun's outer envelope. Venus is consumed next. Venus, already a hellish world, is engulfed by the expanding stellar atmosphere. Earth's fate is the subject of ongoing scientific debate. The key question is whether Earth's orbit expands fast enough. As the Sun loses mass through stellar winds, the gravitational pull decreases and planets spiral outward to stay ahead of the expanding Sun. Or whether Earth is engulfed. The current best models suggest Earth is on the edge. The Sun's maximum expansion will reach approximately 1 astronomical unit, which is exactly where Earth is right now. Some models have Earth surviving, albeit as an unrecognizable cinder of rock, its surface molten, its atmosphere gone. Other models have Earth's orbit not expanding fast enough and the planet spiraling inward into the solar photosphere. Either way, the distinction is moot for any concept of habitability. Earth, in this phase, whether technically surviving outside the Sun or technically inside its outer atmosphere, is a rock at temperatures exceeding 1,000 degrees Celsius. During the red giant phase, something remarkable happens in the outer solar system. The habitable zone, The distance from a star where liquid water can exist on a planet's surface has moved outward dramatically. Jupiter's moon Europa, Saturn's moon Titan, and other outer solar system worlds that were frozen for billions of years are now bathed in intense heat. For perhaps 100 million to a few hundred million years, liquid water may exist on the surface of worlds that were previously ice-covered. If any microbial life had managed to survive in the subsurface oceans of Europa or Enceladus over the previous billions of years, as is at least theoretically possible, those organisms might briefly have surface conditions available to them for the first time. Life somewhere in the solar system might have its last brief window. And then the red giant phase ends. The red giant phase lasts roughly 1 to 2 billion years. During this phase, the Sun loses enormous amounts of mass through intense stellar winds, blowing its outer layers into space in what are called thermal pulses. These pulses happen periodically as the Sun's outer envelope becomes unstable. What remains when the outer layers are fully expelled is a white dwarf, the collapsed core of the Sun, roughly the size of Earth, but containing about half the Sun's current mass and no longer undergoing fusion. It glows white-hot from residual heat, but produces no new energy. It will gradually cool over billions of years. The expelled outer layers of the Sun form a beautiful, expanding shell of glowing gas, a planetary nebula. This structure, visible for roughly 10,000 years before it dissipates, is one of the most striking phenomena in astronomy. Planetary nebulae are the last visible evidence of a star like the Sun, a 10-billion-year life briefly illuminated before fading into cold space. And what of Earth? The most current models suggest that Earth, if it is not already engulfed during peak red giant expansion, will be engulfed during the thermal pulse phase, approximately 7.59 billion years from now. The drag of the Sun's expanded outer atmosphere creates a braking force on Earth's orbit, causing it to spiral inward. Earth crosses into the solar atmosphere. The rock surface vaporizes. Any remaining geological structures are destroyed. The elements that once made up oceans, continents, atmosphere, and every organism that ever lived on this planet are mixed into the outer layers of the dying Sun. Earth, as a discrete object, no longer exists. The white dwarf that the Sun leaves behind will cool for hundreds of billions of years. In the far future, trillions of years from now, it will become a black dwarf, a cold, dark, inert ball of crystallized carbon and oxygen, drifting through space with no light, no heat, no activity. The solar system will be quiet. The planets that survived, Jupiter, Saturn, Uranus, Neptune and their moons, will orbit a cold, dead remnant star. Their surfaces will be frozen near absolute zero. The last vestiges of warmth from the solar system will have dissipated. And somewhere in that cold outer solar system, perhaps on the frozen remains of a moon, there might be preserved molecular evidence of Earth biology. Organic compounds from a time when this solar system had a living world at its center. No one will be there to find it. Let's step back now, all the way back. The universe is 13.8 billion years old. Earth existed for roughly 7.5 billion of those years, more than half of cosmic history. Life existed on Earth for at least 4 billion of those years. Nearly 30% of the total age of the universe. Complex multicellular life, the kind that includes animals, plants and fungi, existed for roughly 600 million years. That is about 4% of the universe's age. Technologically capable, language-using civilization has existed for perhaps 10,000 years. Compared to the age of the universe, that is 0.00007% of cosmic history. Here is what those numbers mean. In the full story of this universe, a story measured in trillions of years, Earth was an extremely brief event, a rocky world at the right distance from a medium-sized star with the right chemistry at the right time, that happened to develop liquid water and self-replicating molecules, and eventually organisms complex enough to look up at the sky and ask where they are. That is not common. There are roughly 200 to 400 billion stars in the Milky Way alone. There are roughly 2 trillion galaxies in the observable universe. The sheer number of possible worlds is staggering. And yet, the specific chain of events that produced Earth, the right star, the right orbit, the right moon to stabilize the axial tilt, the right Jupiter to deflect most large asteroid impacts, the right geological history, the right timing of oxygen production. That specific chain is not guaranteed to repeat. It may be common, it may be rare, we do not yet know. What we do know is that Earth produced life, and that life, for 4 billion years, explored every conceivable niche, developed every conceivable strategy for survival, and produced, at the end of its run, an organism capable of understanding its own situation. That organism looked at the sky and recognized it was a small thing on a small world, orbiting an ordinary star in the outer arm of a galaxy among trillions of galaxies. And it built tools to understand how it got there. And it built more tools to try to stay. Whether we succeed in that, whether we survive our own century, leave this planet, spread into the solar system and beyond, that question is not answered by science. It is answered by what we do. But the planet itself, regardless of what we do, will end. Not by choice, not by failure, by physics. The sun will swell, the oceans will boil, the last microbe will die, the rock will melt. The atoms that were once a living world will become part of a stellar cloud. And from that cloud, eventually, new stars and new planets will form. That is not a tragedy. That is how the universe works. Elements forged in one generation of stars are scattered and used by the next. The carbon in your body was made in the core of a star that exploded before the sun was born. When Earth is absorbed by the sun, its atoms do not disappear. They continue. In some sense, Earth will never be gone, just transformed, redistributed, part of something else. That is the honest end of the story. Not ashes, just change.